Hi everyone, this is Professor Mayunger and you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello, yes. Today I'm going to show shear force and bending moment diagram of a simply supported beam using some incline loading, and also you need to find out maximum stress, its location, and also validate its results using ANSYS Mechanical APDL, right? So let us see the statement of the problem. Draw the shear force and bending moment diagram for the beam shown in figure. Also find maximum deflection and location. The beam is rectangular cross section with depth of 300 mm and width 200 mm. Find maximum stress, its location, and also validate its results using ANSYS Mechanical APDL, and consider modulus of elasticity as 200 gigapascal or 2 into 10 to the power 11 Newton per meter square, and Poisson's ratio as 0.3. So this is the statement of the problem, and we can see that total span of the beam is actually 4 meter. It is supported at two extremities. From left hand side is fixed and right hand side you are having a roller support, and at specific distance of 1 meter from left hand side at an angle of 60 degree we are providing a point load of 100 kN, and from origin at a distance of 2 meter we are providing another point load of 200 kN at an angle of 45 degree, and at a distance of 3 meter from left hand side or origin we are applying another point load of 300 kN at an angle of 30 degree. Now under this loading condition we need to find out the shear force and bending moment diagram of this beam, and also we need to find out the maximum stress, its location, and also the maximum deflection, right? So without wasting time, let us start our analysis using ANSYS Mechanical APDL, right? First of all, we need to create a directory, and in that directory we need to save everything. Next to that, we need to change the title of this one, and that can be done from file, change title. We are keeping the name of this title as FA12. Okay, to see the title, plot replot, and it will show the title at the lower left corner, right? This is visible here right now. Now first of all we need to select what type of analysis it is. That will be done from preferences. In ANSYS Mechanical APDL we need to move from top to bottom from left hand side, and first one it will be preferences. What type of analysis it is, that will be obtained from preferences, right? So preferences, it is a static structural analysis. Okay, next one we need to provide elemental properties, and that will come from preprocessor. So element type, add, edit, delete, we need to add it, and we are considering beam with 3 defined strain with element type reference number is 1, and from options we are selecting that element BY will be cubic form. Okay, let us close it. Next to that we need to provide material properties, right? And material models, structural, linear, elastic, and isotropic. Isotropic means material property remains same in all directions, and as told before, modulus of elasticity of this material is 2 into 10 to the power 11 Newton per meter square, and Poisson's ratio is 0.3, right? So modulus of elasticity is 2E11 and Poisson's ratio is 0.3. Okay, done. Now let us close it. Next to that we need to provide sections of this one. Sections, beam, common sections. It is little bit a different cross section compared to the others one. It is provided that it is having breadth of 200 mm and height of 300 mm, so it will be 0.2 meter breadth and height will be 0.3 meter. Okay, done. Now we need to start modeling, and let us create key points in active coordinate system. First key point will be created at origin, so apply. Second one will be created at a distance of 1 meter from origin, apply. Third one will be created at a distance of 2 meter from origin, apply. Fourth one will be created at a distance of 3 meter from origin, apply. And fifth one will be created at a distance of 4 meter from origin, apply. Excluding these different key points, we need to provide another extra key point for the orientation of the beam. Let us provide the specific location of this special key point at a distance of x equal to 0 and y equal to -3. Okay, we have provided all the necessary key points. Now these key points to be connected in the form of lines. So lines, straight lines. Let us join key point 1 and 2. Next key point 2 and 3. Next key point 3 and 4, and finally key point 4 and 5. All the key points are joined in the form of lines. Okay, next to that we need to start meshing. So mesh attributes, and also while considering mesh attributes we need to consider the extra key point what we created for orientation of the beam, that should be also selected. So let us select all lines, and we need to pick orientation key point also. So let us select key point 6. Okay, done. Now we need to start meshing from size controls, and we can setting manual size, all lines, and number of elemental divisions for each line. We are considering this one as 10. You can make it more for better meshing also, but it is 10 is okay for this moment. Okay, done. Now finally we need to mesh it. Mesh lines, pick all lines are meshed. Meshing is complete. Now we need to apply our boundary conditions, and that will come from loading, right? So load analysis type, it is a new analysis and it is a static structural analysis. Okay, now define loads. Apply structural displacement on key points. Key point 1 will be fixed, so select key point 1, apply. It will be restricted to move along x, y, z, and also its rotation will be restricted along x and y. Apply. And the extreme right hand side key point selected. Okay, again it will be restricted to move along y and z. By the same time it will be restricted rotation along x and y also. Okay, done. Now we need to apply our incline load. Before applying incline load, we need to rotate the key points at the specific locations. So plot lines, you can select the specific location. At these specific locations we need to rotate the key points. So that can be done from modeling, nodes, rotate key points by angles. Let us see the question paper how that must to be rotated. At this location, this point load should be applied at an angle of 60 degree, and the magnitude of this one is actually 100 kilonewton. Second one will be applied at an angle of 45 degree with a magnitude of 200 kilonewton, and the third one will be applied at an angle of 30 degree with a magnitude of 300 kilonewton, right? It is very important to understand the angular orientation of these loads. As we are not applying any kind of orientation, in that case the angle should be 90 degree, that is the load should be applied vertically, right? Let us see the first case. We need to change the orientation, so from 90 degree it will be rotated in the clockwise direction by 30 degree. So it will be minus 30 degree. To have the orientation of the inclined force, in first case we need to change the angle by minus 30 degree, because originally it was in the vertical position. To change the orientation by 60 degree, we need to rotate this one by minus 30 degree. So from this vertical location, it will move in the clockwise direction by 30 degree, then it will come in the second location. Similarly, the second point, without applying any incline load, normally the load will be vertical. So to have this kind of orientation, we need to rotate this point in the clockwise direction by 45 degree. Similarly, the third one, if we are not rotating, normally the angle should be 90 degree. Now to have an orientation of 30 degree, we need to rotate the key point or node by an angle of 60 degree in the clockwise direction, so it will be minus. We can repeat this one again. First point here, the key point or node should be rotated by an angle of minus 30 degree. Second one will be rotated by an angle of minus 45 degree, and third one will be rotated by an angle of minus 60 degree. Okay, so let us do that one. First case, it will be rotated by an angle of minus 30 degree. Apply. Second one, it will be rotated by an angle of 45 degree, so minus 45, apply. And third one, it will be rotated by an angle of minus 60 degree. Okay, it will be minus 60 degree. We have rotated the specific key points or nodes. Now we can apply our loading, right? So we can go back to load again and define loads. Apply structural force on key points. Let us select first key point, apply. Here in this case, we need to apply load in the downward y direction, so it will be minus 100 kilonewton. Apply. First one is made. Now the second one, it will be again selected the next key point, apply. It will be minus 200 kilonewton. Apply. Let us select the third one. Okay, it will be minus 300 kilonewton. Okay, we have applied all the incline loads at specific key points or specific nodes. Okay, now we need to run it, right? So solution, solve current LS. If everything is right, it will show solution is done. Okay, it is showing solution is done, so everything is perfect. We can see our results from general post processing. Okay, let us close it. General post processing, and first of all we need to read results from last set. Next to that, we need to define element table. So element table, define table. Let us add it. Now for this bending moment and shear force, together with that we need to find out this axial thrust and also combine maximum stress and minimum stress. For that we need to define on the specific numbers, right? For bending moment, we need to select SMIS 2 and 15. So let us select from drop down menu by sequence number. It will be SMIC 2, apply, repeat the process again by sequence number, SMIC 15, apply, again repeat the process by sequence number, SMIC 5, apply, by sequence number, SMIC 18, apply, by sequence number, SMIC 1, apply, by sequence number, SMIC 14, apply. Now the last one for this maximum combined stress by sequence number, SMIC 34, apply, by sequence number, SMIC 39. That is for the end node of this maximum combined stress, apply. Now the last one for minimum combined stress, for the first node it will be by sequence number and SMIC 35, it will be by sequence number and SMIC 35, apply. And the last one for the minimum combined stress for the last node by sequence number, it will be SMIC 40. Okay, let us update all these numbers. Let us close it. Now we can see our results. First of all, we'll see results from listing. So list results. First of all, we're going to see shear force and bending moment. So SMS 2 and 15 for bending moment and SMS 5 and 18 for shear force. Okay, so these two data representing bending moment and shear force at specific nodes or specific locations. You can see first two columns represented by SMS 2 and SMS 15 are indicating bending moment at specific nodes, and third and fourth column representing shear force at specific nodes, right? And we can see here maximum bending moment is occurring at node number 20 and 21. It is 0.34617 into 10 to the power 6 Newton meter, and minimum stress is actually occurring at node number 1 and 40. It is minus 0.5488 into 10 to the power minus 8 Newton meter. It is negligible. And you can see maximum shear force is occurring at node number 1. It is 0.21431 into 10 to the power 6 Newton, and minimum shear force is occurring at node number 31. It is minus 0.1638 into 10 to the power 6. Right, so it is negligible. Let us close this one. Next to that, we want to see axial thrust and also maximum and minimum combined stresses. Right, so again, element table data, SMIS 1 and 14, that will represent axial thrust. Then SMIS 34 and 39, that one will represent maximum combined stress. And finally SMIS 35 and 40, that will represent minimum combined stress. Okay, let us see that one. We are having total 40 nodes, and we can see that each different node we are having different values of axial thrust and also maximum and minimum combined stresses. First and second column represented axial thrust at specific nodes. Third and fourth column represented by SMIS 34 and 39 representing maximum combined stress, and the last two columns, fifth and sixth column, represented by SMIS 35 and 40 is representing minimum combined stresses. And from this data, we can see at the last moment that axial thrust is maximum at node number 31. It is 0.6599 into 10 to the power minus 7, and minimum is minus 0.45123 into 10 to the power 6. Next one, we can see maximum combined stress is occurring at node number 20 and 21. It is 0.11389 into 10 to the power 9 Newton per meter square, and minimum combined stress is occurring at node number 1 and 40. It is 0.1829 into 10 to the power minus 5 Newton per meter square, right? So these are very important results. We can save these things, right? Now we want to plot these results. So plot results, can to plot line elemental response. First of all, we want to see shear force and bending moment diagram. So it will be SMIS 2 and SMIS 15 that will represent bending moment diagram. Okay, this is the bending moment diagram, and maximum bending moment is occurring at this location. Maximum bending moment is 0.3416 mega Newton meter, right? It is occurring at this location, right? Okay, next one we'll see shear force diagram. So line elemental response, and it will be SMIS 5 and SMIS 18. You can see that maximum shear force is occurring through this span, and it is 0.214 meganewton, and minimum shear force is occurring through this span, it is minus 0.1638 meganewton, right? Next one, we want to see axial thrust. So it will be SMIs 1 and 14. It is showing that in the left hand side at node number 1, it is minimum, and maximum is at the extreme right hand side, right? And the values are also indicated here itself. And finally, we want to see the maximum combined stress. So it will be SMIs 34 and SMIs 39. This diagram is representing maximum combined stress with indicated values. Maximum values actually, you can see here 0.114 into 10⁻⁹ Newton per meter square, right? And next one, it will be minimum combined stress. So it will be SMIs 35 and SMIs 40. Okay, so this is minimum combined stress. Minimum combined stress is occurring at this location. It is minus 0.114 into 10⁹ Newton per meter square, right? So let us close these things. Next to that, we want to see the animation of this beam. We want to see minimum deflection also. So we can go to list results and nodal solution, DOF solution. We want to see Y component of displacement. Okay, so we are having total 71 nodes, and at each node we can see different values. Maximum deflection is occurring at node number 47. It is minus 0.946 into 10⁻⁻² meter. Now I want to see this deflection in the form of plotting. So plot results, contour plot, nodal solution, and we want to see degrees of freedom solution and Y component of displacement. Let us see that. It is showing at central part we have a deflection of minus 0.00947 meter, and at extreme locations you can see deflection is actually minus 0.001052 meter. Okay, next to that we want to see the animation of this one. Before that, we'll see the beam into 3D format. So plot elements and plot controls, style, size and shape, and display of elements should be on. Okay, this is the beam. Let us see the isometric view for better representation of this beam. So this is the beam with a depth of 300 mm and breadth of 200 mm, or you can say breadth equal to 0.2 meter and depth equal to 0.3 meter, right? Now I want to see the animation of this one. So plot controls, animate, deform results, and with the default setting, we want to see displacement in Y direction, EY. Okay, now to see the deformation or displacement in a better way, let us decrease the delay period. So this way the beam will be vibrating, right? And maximum deflection is occurring at the middle point, and that node is also known. We have already shown that one to listing results, right? So let us close this one. This is all about today's video. This was a very simple finite element analysis of a simply supported beam under some inclined loading. And in this analysis, we have seen the shear force and bending moment diagram, and also we have seen axial thrust and maximum and minimum combined stresses, and also we have found the maximum deformation and maximum deflection in the Y direction, right? So with this one, we'll conclude our today's video. Thank you so much for watching this video. Thank you again. Bye.
If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.